Go ahead.
Okay. Hello again, everybody. I welcome to all of you for joining this meeting, and many special thanks to Mr. Brent Maxfield who accepted our invitation to be the speaker for Friedman Family Visiting Professional. Mr. Maxfield is a professional structural engineer in the Church of Jesus Christ of Latter-day Saints. He has more than 35 years experience in this field, in the field of structural and seismic design of structures. He is a very active member of ERI in Utah, and he is awarded the Utah Engineer of the Year by the Utah Engineering Council. He has several publications in this area, and he has written 3 books in the use and application of PCT MATCAD. I will ask Mr. Maxfield to present us for around 60 minutes. If you have any question, please write down your question in the chat box, and I will read your question after the presentation, and Mr. Maxfield will answer your question. And please try to make yourself muted during the presentation. Thank you so much. Mr. Maxfield, you can start the presentation.
Well, thank you. I appreciate the opportunity of virtually visiting the University of Memphis. It would have been much more enjoyable, I think, for all of us, for me to be able to come there and visit with you in person. But it's very nice that we have this technology that allows us to get together and share some things. And I have enjoyed visiting with some of your students for a half hour and getting to know them a little bit and some of the things that you're doing. I've been very impressed with the work that you're doing at the University of Memphis. So it's a great opportunity for me to visit with you and get to know you and present this lecture and that I'm calling Important Seismic Concepts. So I'm going to share my screen.
1 second. Now, would you everybody mute yourself? We're getting a lot of echoes. Okay, I'm sorry. Go ahead.
Okay, so let me. Okay, so hopefully you're seeing my screen now.
Yes.
Okay, well, I want to talk a little bit about EERI. This lecture is sponsored by EERI, the Earthquake Engineering Research Institute. This was established in 1948. It's the leading organization in the world that brings together a multidisciplinary team of professionals. And it's a great opportunity to be able to be sponsored by ERI to come visit with you. I encourage each of you to consider joining ERI as a student member, and then after you graduate as a young professional and then a professional member. So ERI will reduce earthquake risk by advancing the science and practice of earthquake engineering, improving understanding of the impact of earthquakes on the physical, social, economic, political, and cultural environment, and advocating comprehensive and realistic measures for reducing the harmful effects of earthquakes. It's a pretty broad statement, and it takes more than just engineers to be able to accomplish that. The ERI is comprised of many people, which we'll talk about in just a second. So why belong to ERI? I think the 3 things that are important is that you can connect, learn, and lead. I think the connections that will allow you to meet people from various cultures, various disciplines, and various experiences is a great benefit of joining ERI. You learn from these people as you connect with them, and there's great opportunities that ERI provides for learning. And then I think one of the important things is, especially as you're young in your career, is leading, because you can learn from those people who are leading, and it gives you opportunities to lead. One of your students is a member of the Student Leadership Council, the SLC, and that is a great opportunity for leadership. And so joining ERI gives you that opportunity while you're young in your career to learn and to lead and to connect. So I've been an ERI member for many years. I served for 3 years on the Utah chapter board, our regional chapter here in Salt Lake City. And I was one of those years, I was president of that Utah chapter. And as a member of ERI, I've learned and loved my association with the leaders in the field of earthquake safety. I've gotten to know many of them as friends and mentors. And I've also feel that making a difference is important in my career, and belonging to ERI gives me that opportunity to get out and meet with professionals and to help cause change to happen. So I've really enjoyed my experience with the ERI and feel that it's been a great benefit to me in my career. So you can see that ERI includes many more types of people than just engineers. There's scientists, there's architects, planners, social scientists, public officials, emergency managers. And they all work together because as you probably know, or as you will learn, that solving the earthquake risk is not just an engineering problem. It goes into many different aspects. One of the things that ERI does is the School Earthquake Safety Initiative. It's a program to promote safe buildings for school children via outreach, screening, education, and policy. And if your local student chapter there hasn't gotten involved, if you reach out to the ERI national chapter, they will give you opportunities and some materials that you can actually take out into elementary schools or high schools and help start to teach seismic concepts and also the importance of seismic awareness. Another program that ERI sponsors is the Learning from Earthquake program. Whenever there's a major earthquake somewhere in the world, ERI puts together a team and sends this team out to learn from that event and then distribute that information so those that were not able to visit the actual earthquake can learn from the experiences of others. It's a great thing that ERI provides. And if you go to the learningfromearthquakes.org, you can research many earthquakes that have happened around the world. And one of the really cool things that you can get involved in as students and graduate students is the Learning from Earthquakes Travel Study Program. You can apply through ERI to be a part of a team that will go out and investigate these earthquakes. And it's a great opportunity to learn from the local experts as well as the national and world experts in the field of earthquake engineering. There are also many benefits to joining as a student member. This is the Friedman Family Visiting Professional Program, which we're taking part of here. There's the seismic competitions, the student papers, there's graduate fellowships, there's travel grants to the ERI annual meeting. Hopefully those will start up again next year. This year it's a virtual meeting. And then you get online access to the Earthquake Spectra, which is the journal that ERI produces. So as a student member, which is very inexpensive, you get the benefit of all of these different things. And then after you graduate, you can join the Student Leadership Council, join the Young Member Committee, join a regional chapter. The chapter in your area is the New Madrid chapter. You can mentor seismic design competition teams, apply for the postgraduate fellowship, internship, and apply to be part of the study. By being an ERI member, you demonstrate your commitment to reducing earthquake risk. So as you go out and look for jobs, I think employers will be very impressed that you have been a student member and are actively participating. So your own doctor, Peshnik, is the regional chapter president here in Tennessee. So talk to him after you graduate. If you're going to stay local, be part of that chapter. Help make it successful. Every chapter needs members who are interested in helping to make that chapter successful. By being a student member, you can also get 1 year free of being a young professional member, and then you get reduced rates for the next 4 years. So if you're not a member of your student chapter, I encourage you to reach out to the student chapter and become a member, and it's got great benefits. So there's kind of just a good snapshot of all the different people that are involved in EERI and the different activities. So I appreciate the opportunity of being here, and I'm here because of a generous donation of an endowment by the Friedman family to EERI, and gives student chapters the opportunity of having professionals come out and visit each chapter. Well, I want to start my talk today by talking about my grandkids. These are 2 of my grandkids. I've got 6 grandchildren. I've got another one on the way. That will make 7. But they're great. This picture here is taken when Lexi, on the right in the middle picture, was turning 3. It was taken on her birthday. And her cousin, James, is on the left. Now, James, in this picture, is the day before he turns 2. So he's still 1 in this picture, 1 year and 364 days old. But you can see that James is quite a bit taller than Lexi. And the picture on the lower right was taken just a few days ago. This was just before Lexi turned 6 and James turned 5. So I want to talk about this because I think it's things that you can relate to. As you think about children that you know, or maybe you've experienced being really tall or really short as you've gone through school. Doctors usually, when you go to a doctor, they'll say, Lexi here, for example, she is in the 4th percentile for her height. She's pretty small. So I hope you all have an understanding of what that means. If we were live, I'd probably ask for responses, but let me just kind of give you some responses. The question is, if Lexi goes out into the community and visits with other people that are her age, whether as a 3-year-old or as a 6-year-old, what's the likelihood that she will meet somebody that's taller than her? Well, it's pretty high because she's in the 4th percentile. That means that there's only about 4% of the girls that she meets that are her age that would be smaller than her. So she's pretty tiny. Most of the people she meets are going to be taller than her. Now, James, on the other hand, is tall for his age. He's in the 98th percentile for his height. So if James goes out in the community and visits with people that are his age, whether as a 2-year-old or now as a 5-year-old, most of the kids that he meets are going to be, most of the boys that he meets will be smaller than him because he's in the 98th percentile. So that kind of gives you a sense that Lexi is really small for her age and James is really tall. Now I have another grandson. His name is Liam. He's in this picture as a superhero. He's just a pretty average boy. He's just a boy that just likes to do running and jumping and playing and laughing and giggling. He's pretty average. He's about 50th percentile. So when Liam goes out in the community for boys his age, about half of them will be taller than he is and about half will be shorter than he is. And so I wanted to talk a little bit about my grandkids because I wanted to compare that to earthquakes, because earthquakes are kind of like these kids. We get some earthquakes that cause really high shaking, and we get some earthquakes that cause really low shaking. And for the same earthquake, some areas may see high shaking and some may have low shaking. Because just like kids, there's natural variation in lots of different things. If you think about popcorn and you put popcorn in your microwave, all of that those popcorn kernels don't pop at the same time, do they? You get some that pop at the very beginning, and then you get this big crescendo of popping right in the middle. And then there's always the stragglers that tend to pop a little bit later. And that's natural variation. We can't create popcorn that all pops at the same time, and then you're done. I just put on here Lexi on the left, and I put James on the right, and Liam in the middle. And if I gave every one of you a kernel of popcorn, I don't think you can tell me when that kernel of popcorn is going to pop. But if I ask you a different question, if Lexi's popcorn kernel represents the 4th percentile, and James represents the 98th percentile, and Liam represents the 50th percentile, if I ask you the question, will your kernel of popcorn pop after Lexi's? So what do you think? Pretty likely? Well, it probably would be pretty likely because she represents the 4th percentile of those kernels that pop. And so your kernel would probably pop after Lexi's. Now, if I ask you the same question, would your kernel pop after James' kernel if he represents the 98th percentile? And I think you might be able to understand that, no, it's not very likely that my kernel will pop after James's kernel. But if I give you a kernel and say, is yours going to pop after Liam's? Well, that's a little tougher question because, now you got a 50-50 chance that your kernel will pop after Liam's, or it could pop before Liam's. So your kernel could pop before Lexi, not very likely. It could pop after James, not very likely. And then it's kind of a 50-50 between whether it'll pop before Liam or after Liam. Now, it could be the same thing with light bulbs. I bought, several years ago, Home Depot had light bulbs on sale. These were the old fluorescent style light bulbs. And I thought, wow, these are really cheap. So I bought a couple of cases of them because they were so cheap. And I still have light bulbs left over because these things never burn out. These are 20,000 life hours. Now, does that mean that that bulb is going to burn out at 20,000 hours after I turn it on? Well, we could do an experiment. We could all get a light bulb, turn it on, wait 2.5 years and see what happens. But, light bulbs don't typically tend to burn out at the same time. There's natural variation of when the light bulbs burn out. So I wanted to give you these ideas about natural variation in children, in popcorn, and light bulbs, because when we talk about earthquakes, there's also going to be natural variation in earthquakes. There's lots of words that we can use when we talk about earthquakes and seismic and seismology and structural engineering. A lot of those terms tend to focus around earthquakes and magnitude. What was the earthquake of that earthquake? And the news really likes to talk about magnitude. That's what they tend to focus on. But after my lecture today, I hope you understand and will actually think that, hey, it's really more important to talk about shaking. And I'm going to spend a few minutes talking about shaking and try and move the discussion from earthquakes and magnitude to talking about shaking. And there's two sayings that I like to use that help move that discussion. The first topic is when the earth quakes, the ground shakes. Okay, now that may seem pretty obvious to you, when the earthquake happens, the ground is going to shake. But I want to emphasize that it's the shaking that is important to talk about. And that's the second point, and it's all about the shake in the quake. So by the time I'm done today, hopefully everybody on this call will be able to understand why it's important to say it's all about the shake in the quake. So if we're going to talk about shaking, I think it's important to understand what shaking is. So I'm going to play a video here, and then we'll talk about shaking. Now they just see something happening. So that's a good visual description of shaking. Okay, what magnitude earthquake are these? Well, I don't know what magnitude earthquake they are, but I think we can quantify the level of shaking, and we can describe the shaking. As I've shown this video to other groups, they give me words like, how would you describe the shaking? And it's scary, significant, violent, terrifying. And those are all descriptions that could help give at least some description of the shaking that was in these different videos. But really, it's not so much the magnitude of the earthquake that we're seeing, but the shaking that the earthquake caused to happen. Well, let's see, it wants to go again. We'll play it again. Well, okay, here we go. So I'm going to talk about concepts here. So every time I introduce a concept, I'll list a concept in front of it. The first concept I want to talk about is magnitude. I think we all have a pretty good understanding of magnitude in terms of, hey, a 6 is going to be bigger than a 5, and a 7 is going to be bigger than a 6, and a 9 is a really big magnitude earthquake. I think public likes to talk about magnitude because it's easy. It's got a number. Whenever there's an earthquake, we always like to know what the magnitude is. And that's important. And we'll talk about why magnitude is important in just a minute. But we talk about energy and how some earthquakes are 10 times bigger than other earthquakes in terms of energy. So magnitude really is an energy term, and it talks about how much energy is released. So one of the things that a magnitude can affect is area. I've got two different earthquakes here on the screen. The one on the left was the Christchurch earthquake that happened in 2011. And the one on the right is the Chile earthquake that happened in 2010. Both of these maps are drawn to scale. And the thing I want to show you on the left is that the Christchurch earthquake affected just a small area around Christchurch. It was a magnitude 6.3. The one on the right is a magnitude 8.8, and it happened in Chile, just off the coast. And you can see the area that was affected by that earthquake. The area that was affected by that magnitude 8.8 almost encompasses the entire country of New Zealand. So the larger the magnitude, the more area that will be affected by that earthquake. So that's the first concept about magnitude that I want to convey. The second concept is duration. Larger magnitude earthquakes will cause longer shaking duration. So here's two graphs from a Seattle earthquake in 2001. It was a relatively small earthquake in Seattle, a 6.8. And then we have on the bottom, the 9.1 Japan earthquake. And you can see that that earthquake in Japan lasted minutes, while the earthquake in Seattle lasted for seconds. And so larger magnitude earthquakes tend to last longer in terms of the shaking than small magnitude earthquakes. So those are two things that we can say that are true about magnitude. It affects bigger area, the larger you get, and it's going to tend to shake longer, the larger the magnitude gets. So we can say that a specific magnitude earthquake does not equal a specific level of shaking, and we'll talk about that in just a minute. And it is true that larger magnitude earthquakes have a potential for larger shaking. In other words, the mean, as you go up in magnitude, the mean increases. But we're going to talk up in just a minute about the range of shaking that's potential for different magnitude earthquakes. And we're going to see that it's all about the shake and the quake. Now, let me give you an example. So the picture on the left was taken in Christchurch, New Zealand, just about a week before their magnitude 6.3 earthquake. The picture on the right is taken a year or so after the earthquake. And it shows how many buildings that were torn down due to extensive damage. So this was a 6.3 earthquake, and it's typically, you never hear on the news about magnitude 6.3 earthquakes. They're usually pretty small. They don't cause a lot of problems. This was a magnitude 6.3 earthquake that caused a lot of problems. And it's because the shaking intensity underneath Christchurch was very large. I was in Christchurch about a year ago, just over a year ago, and I still saw the damage that was caused by this earthquake. They're still dealing with the effects of a magnitude 6.3 earthquake in Christchurch. So just knowing the magnitude of an earthquake is not enough. We have to move the conversation from earthquakes and magnitude to shaking. And as you'll hear many times in my presentation, it's all about the shake and the quake. So the USGS uses an intensity scale to help quantify the level of shaking that occurs in earthquakes. And you can see that there's numbers, Roman numerals, there are descriptions of shaking, and there's colors that are used to define the shaking. And let me just show you how the USGS produces these shaking intensities. It's called a shake map. These are produced after most significant earthquakes around the world. The USGS will put out a shake map. It's a contour map, just like as you look at mountains on a contour map. The contours tend to focus you on where the greatest shaking occurred. So here in Christchurch, you'll notice that there are several triangles that are colored red, which, as we saw in the description before, that those are violent shaking streams. And then it tends to diminish quite rapidly outside of downtown Christchurch. So here we have a small earthquake that caused violent shaking. And that's going to say, okay, this earthquake caused shaking that's going to be more over towards the James area of the shaking scale. And violent shaking under a populated area is a bad thing. And when you get violent shaking in a populated area, you will tend to see quite a bit of damage. So here's a shake map of the Blbo, Chile magnitude 8.8 earthquake from 2010. And I want to talk about many things that we look at as we see this map. And it'll capture, I think, some of the things that we've talked about. Let's first look at the scale for the 50-kilometer and 50-mile range on the bottom of the screen. We learned earlier that large magnitude earthquakes are felt over a much larger area. This earthquake was felt over hundreds of square kilometers, whereas the Christchurch earthquake was felt over just a small area. The other thing we learned today is that large magnitude earthquakes last longer than smaller magnitude earthquakes. The Christchurch earthquake lasted for about 10 seconds, and the shaking from this earthquake lasted for more than 3 minutes. Now let's look at these contours. You'll see that there are some red contours out left of the island or the continent out in the ocean, but most of the contours and colors that we're seeing in this big area are in the yellow and orange colors. There are very few red colors in this map. So the violent shaking did not occur in this earthquake. Now, I'm not saying that this wasn't a significant event, because it was, and it's significant because it lasted for a long time. It's significant because it affected so many people and so many communities and cities. But can you imagine how much different this earthquake would have been had we seen red dots instead of orange and yellow dots? So here I want to again focus that we've got to understand magnitude, because it tells us how big an area it affects and how long the shaking goes on for. But we need to know more. We need to know what the shaking level is. So as I've described before, as the intensity gets larger, we tend to see more damage to buildings. And that's important to understand, that if we get a red shaking in a populated area, it's going to be a big deal. And whenever you get an earthquake, it's important to understand what that shaking is. I've got an alert on my phone whenever there's a magnitude 7 earthquake somewhere in the world. It sends me a message that says, hey, there's a magnitude 7 earthquake. When I get that, the first thing I do is I go to the shake map to understand how bad was the shaking, and was that shaking near a populated area. So let me just give you a hypothetical headline. And this is actually not hypothetical, because we did get a magnitude 7 earthquake in Anchorage just a few years back. Magnitude 7 earthquake strikes Anchorage. How much information does that give you? Well, it tells you that you've got a magnitude 7 earthquake. You know that it's going to create a pretty good size area of shaking. You'll know that that earthquake shaking went on for at least a period of seconds, may not be minutes like we would get in an 8 or 9, but it doesn't tell us how big of an earthquake this is. When I got the alert that this magnitude earthquake happened in Anchorage, I quickly went to the USGS site to understand its implications. And then I went to my boss and I says, so a magnitude 7 earthquake just happened in Anchorage. Is it a big deal or not? And he looked at me and he says, well, I don't know. How bad was the shaking? And I went, yes, you understand the message. You have to understand the shaking before you can understand its impact. So here's the contours from the magnitude 7.1 earthquake in Anchorage. And you'll see that most of those are in yellows and oranges. So it wasn't as big of a deal as it could have been. So let's look at another hypothetical headline. Magnitude 7.0 earthquake strikes Anchorage. Most areas thankfully experience light shaking intensity. Or perhaps it could have been this. Luckily it wasn't. Magnitude 7 earthquake strikes Anchorage, large areas of extreme shaking. So those give you a lot more detail, because now you understand quickly that it's a level of shaking that tells us how impactful that earthquake would be. So let's just look at a hypothetical magnitude 7 earthquake. How big is the shaking going to be in a magnitude 7 earthquake? And as I introduced earlier in this presentation, earthquakes behave like children. They behave like popcorn. They behave like light bulbs. It's impossible for anyone to predict what the exact shaking will be from any specific earthquake in any specific area. But we can predict ranges, and we can predict medians, and we can predict standard deviations. So we can understand the likelihood of certain levels of shaking that would be exceeded. So there's also things, and I think many of you that are studying ground motions understand that there are things that we can do that would help narrow that range. If we understand the distance from faults, we can help narrow that range. If we understand the types of soils that are underneath the site, we can help narrow that range. If we understand the rock that is underneath the site, we can understand and narrow that range. So we know it's very likely that shaking intensity will exceed the Lexi level. If we say Lexi represents the 4th percentile of earthquake shaking, we know that a magnitude 7 earthquake would tend to exceed that, most likely. We could also calculate a 98th percentile shaking level and put James there, and that magnitude 7 earthquake would most likely not exceed James level of shaking. We can predict the median. We could say this level of this magnitude earthquake will give you a 50-50 chance that it'll be greater than where Liam is, and a 50-50 chance that it would be less than Liam is. So there are things that we can do to help understand levels of shaking from specific earthquakes, but no matter how tight we squeeze it, there's always going to be a natural variation in that level of shaking. Now that could happen, say 1 magnitude 7 earthquake in an area causes pretty high shaking, and then another earthquake happens and it causes pretty low shaking. It could also be that a magnitude 7 earthquake causes high shaking in one area, but low shaking in another area. So we could have this variability from event to event, or in the same event, we could get variability in the level of shaking. And that's all part of the uncertainty that I'm sure many of you are studying as you research earthquakes. So where do we set it? Well, it could vary and go down, it could go up. It's all dependent upon the various variables that we put into these equations. We can narrow that variability, we can move it to the left, we can move it to the right, but there is always going to be a variability. Now, building codes have to address this variability. How do building codes set a level of shaking that a building has to be designed to? Well, that's what I'm going to talk about here for just a few minutes, because building officials have to set variability. We have to set a level of shaking. So we call that level of shaking that the code sets, we call it the MCER. And that stands for Maximum Considered Earthquake Risk Reduced. And it's a level of shaking, it's an acceleration level that the code says, this is what it is. And you pull it out of a table or off the internet, go to a hazard site, put in your latitude and longitude, and you'll get that level. Those are typically called SS values and S1 values. But that could be set in different places. Now, you'll get a lot of engineers that call this the earthquake, the MCE earthquake. But it's not an earthquake, it's a shaking level, it's an acceleration, which begs the question, if it's a shaking level, why did they call it the maximum considered earthquake? I think that was a bad thing to do, because it has so many people in the public and structural engineers out there talking about the maximum considered earthquake, because it is not a specific earthquake, it's a specific level of shaking. And I would have called it something like the maximum considered earthquake shaking or something like that, or acceleration, but not earthquake. And some of the old commentaries used to call it the earthquake. The new commentaries are pretty clear and concise about that, referring to it as an acceleration or a response acceleration. But I want to give you a challenge. As you talk about earthquakes, make sure that you are clear that as we design, that we design to a shaking level, an acceleration level, and not to a specific earthquake. And the other thing is they call it the maximum considered earthquake. That also kind of gives an impression that if you design to this level of shaking, you're protected from levels of shaking that would happen above this. And if I had my druthers, I'd call it the minimum considered earthquake, which would say this is the minimum value that the code allows you to design to. There are shaking levels that will or could exceed this level of shaking, but this is the minimum. You can't go below this if you're going to design a building. And so those are just some of my thoughts as we talk about code design, and where a lot of the communication, I think, starts to fall down. So this is the minimum that is allowed by the code. And that's why I like to call it the minimum considered earthquake shaking rather than the maximum. And whenever you use this term, I always use the term shaking or acceleration or something after this MCER. So we're always being consistent and clear that MCER is a shaking level. So how do they set it? Well, if you move it left, you're going to get some reduced cost, but you're going to have increased risk. So how far down do code officials like to put it, or would they feel comfortable putting it? And if they move it to the right, you reduce your risk, but you also increase the cost of the buildings. And I'm going to talk specifically about Tennessee here in just a little bit, because I think this is an important discussion. because you're kind of very similar to where we are on the Wasatch Front with the Wasatch Fault. So the question here is, when we set a level that we design buildings to, it's set, the code writers set it so that there's a 1 in 5,000 probability that that ground shaking will cause the collapse of your building. And so it's a collapse risk that they use to set that probability. So that's not a very high probability that your specific building will collapse, 1 in 5,000 any particular year. And if that earthquake happens that causes that acceleration, your building should have no more than 10% probability of collapse. So that's how the code writers said it. They kind of balanced between increased risk and reduced risk, increased cost and reduced cost, and said, okay, we're comfortable that if we set our building design here, that we've got a 1 in 5,000 probability of 1 over 5,000 probability of collapse in any year, and that if the earthquake happens, we won't have more than 10% probability of collapse. So let's look at your engineering and science building here on campus. This is from the ATC hazards website. There are several sites out there that will give you these hazards. They all get their data from the USGS. The MCER values for acceleration, the SS is 0.928. That's for a 0.2 second response. And the S1 value is 0.311 for the 1.0 second response. And I just because I wanted to eliminate the soil effects, I chose a 760 meters per second BC boundary to pull these values up. That sets the FA and FV value equal to 1 if you've done any earthquake engineering classes yet. But anyway, these are two values that the USGS says you have to design to these. Here again, like I like to say, these are the minimum values that you can consider. There is a potential for higher shaking, and I'll talk about that in just a minute. So here we've set the MCER for a 0.2 second response as 0.928. And if you design a building for that level and you get that level of shaking in a future earthquake, you should have no more than 10% probability of collapse. Now, the code writers also put in the code these values right here. This is called the factor deterministic acceleration value for 0.2 seconds. Now that number is 2.467. And if you look at the 1 second, it's 0.787. What that says is that if you get an earthquake, most likely the earthquake on the New Madrid Fault, which is your most famous fault there, that fault is capable of generating very large accelerations. If you look over here on the right, I did a ratio of the deterministic actual event happening, and this is the 84th percentile, so it's kind of up towards James, not all the way to James, because James is 2 standard deviations above the mean, and this is 1 standard deviation above the mean. It's 2.6 times greater than what the code requires you to design to for this MCER. And if you look at the 1 second, it's about 2.5. Because the code says you can take the lower of this probabilistic MCER and the deterministic. And in a case in Memphis, this value is quite a bit lower than that, or actual earthquake. And we have the same issue here in Salt Lake. We're about the same way that you are. And it's important to understand that we designed to this MCER, but there is a potential for shaking in Memphis that greatly exceeds that MCER. And the code writers had to use some judgment in setting an MCER for Memphis. They had to do the same thing for Salt Lake. They had to do it for Los Angeles, New York, Seattle, all of those areas. They use this criteria to set a 1 over 5,000 year probability of collapse. But that doesn't say that there's not going to be an earthquake sometime in the future that will cause accelerations greater than that. So there's the 84th in Memphis, the 2.468 compared to the code value of 0.928. And here's a map that the USGS produced that shows the risk of, well, basically the earthquake codes in the US are based upon this map right here. And it shows that if you moved up to northern Tennessee along the Mississippi River, you would be designing to some pretty significant shaking intensities. Luckily in Memphis, the values aren't quite as high as they are up north, where they're in that range of 2.5 times greater than they are in Memphis. You'll notice in California, along some of those active faults, they've got red there. Basically, it says that these are the probabilities that the shaking will exceed a certain value over a certain time period. It does not say that the shaking will ever exceed these. It just says, based upon the criteria of the code, this is how we're going to distribute the risk around the country. So now that we understand how the building codes are set up in terms of our design values, let's talk about the concept of building performance. The goal is to keep people from being crushed by collapsed buildings. So that's why we set that MCER shaking level. The code said that there should be no more than a 10% probability of collapse if an earthquake occurs and causes the MCER shaking intensity. Aftershocks, however, could cause the building to collapse. I'm going to play this video here. Now that's a pretty scary video. We're seeing big concrete panels falling off of a building. If people had been under those, they would have been crushed. Now, the building code says that during an MCER shaking, we could get architectural components falling off of a building. And some of those elements could cause people to die. They call that a localized death. And the code allows that to happen during the MCER. It allows concrete and stone cladding to fall off of buildings. This building on the left here has got quite a bit of damage. It is at risk of collapse in an aftershock. And so it has been red tagged. You can't go in that building because it's a danger of collapse. But it served the purpose. It allowed people to get out of the building without the building being collapsed. Now, we've talked about this MCER. That's a pretty intense level of shaking. The code says, let's take 2/3 of that value, and we want to see better performing buildings. We want to see things that are better performance. So if we experience that level of shaking, we would expect to see much better performance than what I just described at MCE. So here's some possible damage from a design level shaking. And I put in here design in capital letters and quotes, because sometimes we talk about designing for earthquakes and it's not really clear. But in terms of the code, the design level shaking is very clear. It's that 2/3 MCER. So when I talk about design, I want to connotate a level of shaking that's 2/3 MCER. So let's talk about life safety. It's damaged structural systems. The building could be out of plumb. You could have damaged cladding, but not collapse. You could have damaged interior finishes of walls, ceilings, and floors. You could have damaged HVAC ducts and equipment. Your repair time could be up to years. It may not be economical to repair, and it's most likely that you will not be able to occupy the building during the repairs. And engineers refer to this as a life safety performance. Here again, I put that in quotes because that's a very specific level of performance that engineers like to do and refer to. Now, if you have an essential facility, such as a hospital or a police station, those buildings are expected to be operational after this 2/3 MCE level design shaking. It doesn't mean that that hospital or fire station will be operational if it sees shaking above the design level shaking, that 2/3 MCE. And I think we as engineers, we don't convey that well enough to the general public. We just tend to say, this building needs to be operational after the earthquake or after an earthquake. And we don't specifically say, here's a point along a continuum that we want this building to stay operational at. We always just kind of generalize it, and we're not very specific about saying this building wants to be operational, and we're going to say at this level of shaking. So when you talk building performance, always talk about two things. One, the performance, but number two is talk about the level of shaking that performance will be achieved at. And so we've talked two things. We've talked life safety at 2/3 MCER, and we've talked about collapse prevention. Did I say that right? Life safety at 2/3 MCER and collapse prevention at MCER. And by putting both of those things together, we can define performance, and you can't do it with just one of those terms. So the next concept I want to talk about is ductility. Ductility is sometimes a tough word to understand. Basically, it means bending without breaking, and yielding without breaking, and brittle means that once it breaks, it loses strength quickly. So I just showed a picture of a pencil here that it's pretty strong. If you take a wooden pencil, just put a lot of force on it, and it's not going to break. And then at some point, you'll push it too far, and it will immediately break. It doesn't bend gradually, it just fractures. And that's what we mean by brittle. So when I talk ductility, I want you to think about those two examples, pencils or paper clips. The next concept I want to talk about is R. Now, if you're in structural engineering, and if you've had seismic classes, you'll have talked about R. So if you are not in structural engineering and you haven't talked about R, I'm going to try and stay pretty high level, but I want you to understand how engineers go about designing your building. The R is the response modification coefficient. It's a number that varies between 1 and 8, and it has very specific detailing requirements. And we'll talk about that in just a minute. The R values allows calculations to occur in the elastic range where building deflections are proportional to applied forces. As engineers, we like to have simple equations that allow us to calculate things. And by using this R value, it allows us to stay in fairly simple calculations. Okay, so higher ductility systems have an R that varies between 5 and 8. Sometimes they use the word special, and it allows the building to bend without breaking. Now, lower ductility systems have an R that varies anywhere between 1 and 5. Sometimes they use the terms ordinary. Sometimes they use the term R equals 3 systems, where there are no detailing requirements. And these buildings result in a quicker loss of strength. And I'll show you how the R value is used in our building designs. So we've talked about MCER, shaking. You can see that that's pretty high in this case. We've talked about the design. That's 2/3 of MCER. And now we're going to talk about a calculation level, which is that 2/3 divided by R. So in this case, I used an R of 6, and you can see that there's a pretty significant reduction from MCER to design to calculation. And it really begs the question, why are we designing for forces that are so much lower than we know could be developed? And that's what I hope to, in a simple way, convey here in just a few minutes. So shaking and deformations or drift will be larger than calculated. And let me explain why. So we started MCER, we multiply that by 2/3 to come up to our design level. And now we're going to take that level and we're going to divide that by R. So now our calculation level is quite low. But it allows us to do our calculations in the elastic range. So if we want to calculate our drift, we just put some forces on there, and knowing the stiffness of the building, we can calculate a deformation. Now that deformation isn't reality what's going to happen to your building. It's just an easy way for us to calculate a calculated drift or lateral deformation. In order to get our actual deformation, we need to multiply it by what we call a CD factor. And the code gives you what that factor is. But basically, if you went over to that value of small delta x, it would be equivalent to having a building that was designed to be super, super strong and not yield under the 2/3 MCE level shaking. And that's what I've kind of implied there by these lines, is to say, if I designed this building not to yield and then calculated the drift, that's the number I would get. But because we like to do things simply, we say we're going to move all of our forces down to an elastic range, and then we'll use factors to give us up to what we anticipate the lateral deformation of that building would be. So the point I want to make here is when you calculate a deformation, do not think that that is what that level of shaking will actually cause that building to deform to. We have to use that CD factor to get that anticipated movement. And I want to just introduce two terms here. I'm not going to spend much time on it. I'll come back to these in just a couple of slides. One is called the overstrength, and one is called the ductility. And by combining both of those terms, the overstrength and the ductility, it kind of sets the value for R. If you've got higher ductility, you can use a larger R. And how much ductility you need is going to be a function of how much overstrength the building has. And then the code doesn't give us criteria for estimating deflections in an MCER shaking level. But if you just throw approximately 1.5 factor on there, it'll kind of give you a sense of maybe where that building could go for its deformation if the building sees the MCER level shaking. So what we're doing is we're calculating everything down here, but because of our ductility inherent in the R and the code requirements for detailing, we're able to get a building that's going to get adequate performance for both the design level shaking, which gives us that life safety, and the MCER, which will give us collapse prevention. So even though we're doing numbers here, we expect to see the performance that the code requires by using these factors. So there's the R, the CD, the omega, and the RD factors that the code uses. So let's talk a little bit about nonlinear behavior, because that's what allows us to use the R value. And so what I've shown here is at a point, if you take a building and you push it to a certain point, particular elements of that building will start to yield, but all of the elements don't yield. You can push it a little bit further and another element will yield. And every time one of those elements yield, the building becomes less stiff. And so we have to change the slope of that stiffness. And eventually you'll reach a point where the building just doesn't have any more ability to gain strength, and then it starts to lose strength. And so our modern codes allow us to design to lower strength because of nonlinear behavior. Now that nonlinear behavior also causes building damage. And that's why I talked about some of that damage that we could see after the design level shaking. We could see the building not being plumb. We could see a lot of the interior finishes that are damaged or starting to fail because we're pushing the building way beyond our calculated design levels and getting up into this nonlinear behavior. So nonlinear behavior is an important concept in modern seismic design. So let's just go through a quick ground motion summary. We got MCER level shaking. We reduce that to 2/3. We divide that by R to get our calculation level shaking. And here's some of the assumptions in the building code. The R is used to reduce design to an elastic range where we like it because engineers like simple. And if you size the lateral system using calculation level elastic forces, the building respond as expected with some reserve strength to resist aftershocks at the design level shaking. If the building responds as expected at design shaking, there is a low probability of collapse at MCER shaking, no more than a 10% probability. So let me give you this concept again. The design shaking level divided by R, base shear, is used to size the lateral resisting elements such as brace frames, moment frames, or shear walls. So when we calculate our calculations, that tells us how strong our braces need to be, how strong our moment frames need to be, or how strong our shear walls need to be. And then everything that connects to that yielding element needs to be stronger than that, because we don't want those elements to yield. So I've illustrated that here by a brace frame. We size the brace frame based on calculated force, and then we've maybe have a drag strut that connects to the brace frame, and that calculated force has to be increased by that omega factor. And so those are, take your calculated force, multiply it by the omega factor. And as I showed before, this overstrength factor is what the code says you have to design that to. So if I take that drag strut, I have to make it stronger because this building is actually going to be stronger than what I calculate it's going to be, and that's the overstrength. So let's just review now some of the important seismic concepts that I've introduced today. Engineers design for shaking or ground motion, not earthquakes. It's all about the shake in the quake. Just knowing magnitude doesn't help us. Magnitude affects area and duration. And earthquakes follow natural variability. We can only predict a range of ground motions from a specific magnitude earthquake. We can predict the median, we can predict standard deviations, and anything in between. MCER shaking is a uniform risk of collapse, and that is set to give you 1/5,000 probability of building collapse in 5,000 years, 1/5,000 per year. The MCER shaking is set for a collapse. There we go, 1/5,000 per year. The 84th percentile shaking for a New Madrid fault earthquake is up to twice the MCER shaking. And that says basically that if you get that fault in Memphis, you've got about a 50% probability that the ground shaking will exceed what the MCER tells you to design for. So that's a little bit scary if you get that earthquake, that the shaking that you get has a more than 50% chance of being exceeded. The design shaking is where most code performance requirements are set. So in other words, a hospital is operational and drift limits are set at that 2/3 MCER. If a risk category 2 building experiences the MCER shaking, it should have no more than a 10% probability of collapse. If the ground motion doubles, the risk of collapse increases to about 50%. It's actually 45% if you look at the fragility curve. The R is the response modification coefficient. It allows inelastic performance to be calculated in the elastic range, and that's where engineers like it. It's very tough to do nonlinear analysis. R can vary between 1 and 8. R accounts for ductility. Our CS, our calculated force level drifts, do not equal our expected drifts because you must use the CD amplification factor to get your estimate of expected drift. Low ductility buildings are not allowed in high seismic zones because they lose strength compared to ductile buildings. So in high seismic areas where there's a risk of those larger shaking levels, we want ductility. We want the buildings to be able to bend without breaking and not lose strength. And high ductility buildings are expected to experience and withstand high ductility demand. And ground motions are not an exact science, as I think many of you are understanding. There is a possibility for considerable variation. So I've talked about a lot of concepts today. I hope that maybe some of those concepts that maybe if you haven't learned, as you start to learn them, they'll start to make sense because of this presentation. Hopefully those of you that have taken earthquake engineering classes will be able to say, oh, now that makes sense. And then hopefully if maybe you're a practicing engineers, you've learned something that will be beneficial as well. So I am grateful for this time to visit with you. I've reserved some time now to answer questions. I'll turn the time back over to the student moderators, and I'll stop my screen sharing, and I'm happy to entertain questions.
Okay, thank you, Mr. Maxfield, for your great presentation. If anyone has any question, you can unmute yourself and ask your question, or you can write your question in the chat part, and I will read your question for Mr. Maxfield.
I have a question. So what would you say are some of the most significant developments in, I guess, the field of earthquake engineering within the last couple of years?
Well, let me extend that to beyond the last couple of years. I think one of the things that is really benefiting seismic design is nonlinear analysis. We've been doing it for a long time, but I think it's becoming more and more common for engineers to be able to do nonlinear analysis, because everything I described to you today, using those R values and the importance factors and all of that, is just a way for engineers to try and stay simple in their design calculations. Once you start to put in those actual properties of the building and the nonlinear behaviors of the building, it allows you to better capture the performance of the building and helps you understand, is my probability of collapse going to be 10%, or is it going to be less, or is it going to be considerably higher? And then you can start to making decisions about how to make the building stronger by looking at just specific areas rather than arbitrarily increasing everything in the building for a higher strength. The nonlinear analysis can show you actually where your weaknesses are, and then you can then focus on those weaknesses.
Great, thank you.
Okay. The next question is, what are the gaps between structural engineers, geotechnical engineers, and seismologists?
That is a great question. Everybody likes to play in their own sandbox. And they don't tend to work together. I've talked to seismologists. I've talked to numerous seismologists, and they understand ground motions very well. And they're very good at telling us the ranges of those ground motions that I described earlier. But very few of them understand actually how we take those ground motions that they give us and actually use them. I still remember my conversation with one seismologist, and I told him how we take let's say that 84th percentile ground motion and how we reduce it by 2/3 to design our buildings, and then how we divide that by an R value to design our buildings. And he just stuck there and shook his head and go, why? We give you what these ground motions are going to be. Why reduce all of them down? And so he didn't understand that. And structural engineers have very little understanding about how ground motions are calculated. Many structural engineers just think that the ground motion that we get by the code is the maximum ground motion that site could ever see. And so it's very tough to get all of these groups together and understand each other's perspective so that we can talk and have these discussions. And that's what I like about EERI. EERI gets everybody playing in the same sandbox instead of different sandboxes, because we can have these interdisciplinary discussions. And when you go to an EERI convention, everybody's in the same room and hearing each other's discussions, even though it may not be extremely applicable to what you're doing. I think by learning about what others are doing, it's very helpful. And so One of the things that I try to do is bring everybody together. I try and bridge that gap. And I hope I was able to do that in this discussion by talking a little bit about the seismology and bring it into how the code uses that seismology. So it's difficult to understand. It's something that's an ongoing effort, and I don't think I'm going to solve that problem, but I encourage you to get outside of your sandbox and understand what others are doing.
Thank you, Mr. Maxfield. Any other questions?
Let me ask you a few questions, and maybe you can respond either by chat or by, I got to just turn my chat on so I can see some of your responses. Just 1 second. I've got 2 screens, so I'm just trying to get my screens oriented. There we go. Okay, so let me ask you a couple of questions. Let me get I adjusted my monitor. Okay. So tell me what's more important to understand in an earthquake, magnitude or shaking? And tell me why you think that. And they're both important. I'm not saying neither one is important, but so just defend your response, and either one could be correct.
They're going to get a grade for this, right? Malish answered the question.
So I would think the shaking would be more important than the magnitude, because the magnitude, while the magnitude gives us the duration of the earthquake and how large of an earthquake it is, for the structures that we design, we need to know how much the ground shakes so that we can design it to resist that shaking. So I think it is more important to know the shaking of the earthquake than the actual magnitude.
Okay, so from a structural engineering perspective and a building performance perspective, shaking is more important because it tells us how that building will perform, or maybe it tells us a specific earthquake, how that building did perform because we understand the shaking that happened. Now, so from a structural perspective, that's important. What if you're an emergency manager, which is more important?
Money.
And you could probably argue either side on this.
Mike Sheridan answered that question.
So anybody want to take a stab at that? If you're an emergency manager and had an earthquake, would you want to know more about the magnitude or the ground shaking? And let me just say that both of those are accurate. I think for an emergency management, you want to know both. And why would you want to know magnitude, for example, if you're an emergency manager?
Well, you want to know the areas that are going to be affected.
Exactly. It tells you how big of a deal is this? Am I going to have to deal with this over a length of 100 miles, or am I going to deal with this over a length of 50 miles or 200 miles? So by understanding the magnitude, you can quickly understand this is a big deal for me because it's a magnitude 8 earthquake or magnitude 7 earthquake. It gives you a sense of that area. Now, on the terms of shaking level, it would also say, hey, it's important for me to understand where the areas of strongest shaking occurred. Because if I can look on a map and say, this part of my community had high shaking, now I can immediately send people to that area of high shaking without having any reconnaissance on the ground. because I know that high shaking is going to cause high damage in areas. So as an emergency manager, if I can quickly get a shake map, I know where to send my resources even before I get reconnaissance. Okay, so any other things about shaking and magnitude? I think that's an important concept that we really, as engineers, need to move the conversation into shaking and focus on any of our discussions about building performance or codes. We need to make sure that our conversations are grounded in a shaking level rather than a magnitude level. Any other questions about that? Then I'll maybe talk about some other concepts.
There's another question, Mr. Maxfield. The question is, are the earthquake demand spectrums are realistic in areas with significant side effects?
Okay, so the spectrum is kind of that, if you don't know what that spectrum is, it's kind of that curve that I showed you that starts with a horizontal plateau and then starts to drop down as the period gets larger. So as buildings get taller, the demand or forces on those buildings tend to get smaller. So that's a spectrum. And so short period buildings tend to have higher design level forces. Longer period buildings tend to have lower seismic design forces. So now when we talk about side effects, the code tries to address as many side effects as they can. In the past or currently, we use site factors like the FA and the FV values that help us understand side effects. So softer soils tend to affect different types of buildings differently, and stiffer soils tend to affect stiffer buildings differently. And so we have these factors, the FA and the FB factors, that help address side effects. And the codes do, well, let me say this. Past codes did a pretty poor job in estimating side effects for long period buildings. And the code officials have recognized that for a few code cycles. And in the current code cycle that we're currently in, it made some modifications to those side effects by requiring some site-specific hazard analyses so that we could better capture those side effects, because they found that we were being unconservative in long period buildings. Now the codes that are coming out, the NEHR provisions that were just published just this year, I believe, or the end of last year, are helping to address that, because they're trying to include side effects in the spectrum itself. So we won't need an FA value and an FB value to arbitrarily adjust our spectrum. The spectrum itself will include those FA and FB values in it. So when the next building code comes out, you won't have to worry about FA and FB, but we'll be calculating we'll be calculating points on the spectrum instead of two of them, which we currently do, the 0.2 second response and the 1.0 second response. They'll be giving you periods, like 15 different periods across that spectrum. So the current ones are not really realistic. The FA and FB try to make a pretty good estimate of those, but in the future, we'll be much more able to capture those side effects. I hope that answers the question, but let me give you another side effects that the code doesn't capture, and that is near fault effects, where the building code doesn't capture some of the effects that could actually happen close by a fault. So in Utah, for example, if we're on the Wasatch Fault, some of those near side effects aren't captured very well by the building code, and a site-specific hazard analysis is much better able to capture those side effects. So great question.
Thank you, Mr. Maxfield.
So let me throw
Any
a
other
question
question?
out. Oh,
Okay, you can go on.
let me throw a question out to you because it's the same question I like to ask in Utah, because Salt Lake City sits right along the Wasatch Fault, which is a very large fault. It can generate very sizable ground motions. It doesn't happen very often. It occurs about once every 1,250 years. So it's a low probability, high consequence fault. The way the building code sets ground motions is this 1/5,000 probability of occurrence in any year. Now, if the Wasatch Fault happened to rupture more frequently, say once every 500 years, there would be a much higher probability of collapse for buildings in Utah. And therefore, we would have to design to a higher level of force because that probability of collapse would go up by reducing the recurrence interval of the fault. So right now, we designed to a lower ground motion than what the Wasatch Fault could generate. And as I was looking at your faults in, your MCER in Memphis compared to what the New Madrid Fault will generate, it's about 2.5 times greater. So if you were a code official, would you say, hey, you know, Memphis really ought to be addressing some of the faults that this New Madrid earthquake could give us rather than staying down at the 0.9? If you were the code official for a day, would you say, hey, you know, we're good? Or would you say, well, maybe we ought to think about the possibility of this earthquake and what it could do to us? It's a decision that code writers wrestle with all the time. Decreased cost, increased risk. Increased cost reduces your risk. How about Zoya? You're a seismologist studying ground motion.
Yes, yes, sir.
It's a tough question. Julie Fair would be the one that could answer this. Julie, are you online? I don't see her. Well, the problem is that the code is using the minimum of deterministic and probabilistic. And it was set for California, otherwise they would have been such a big numbers to design. Since the code requires the minimum, and the code officials here, they could follow the code requirements. So using the probabilistic seismic hazard versus deterministic, which is lower, they satisfy the code requirement.
Right.
Yes, I think for infrastructures, they consider the conservative solution, and but for buildings, it's different. It's my primary knowledge about that.
Yeah.
And the other thing is we don't know where the faults are in New Madrid. We don't have the distinguished location of faults. So it's not like Andrea's fault that you know where the fault is. We don't know.
Yes,
Yeah.
for most of the central and eastern part, we don't have the exact location of the causative faults of earthquake.
So it basically gets to, it's not a simple answer. There's a lot of uncertainty that goes into this. And we have to make some determinations. And so the code writers have set a specific number for the University of Memphis. They've set the same, used the same criteria to set the values that I have to design a building for in Salt Lake City. And they use that same criteria for a building in California. So they're using consistent criteria, but specific areas may have some questions about whether they want to follow that. In fact, in Utah, we're in the discussions phase right now of, are we happy with where the code requires us to put buildings, or design our buildings for? Because in Salt Lake, our MCER is about the median shaking on the Wasatch Fault earthquake. And so some areas could receive higher than median shaking, and that puts them above MCER. So it's a real question that we're struggling with, because the code writers have said this is the criteria that we're using to set your ground motion. And if you as a community feel like you're not being well enough protected, you can change it locally. And so that's kind of the question that we're wrestling with right now.
Well, I think we need to end the meeting. We really appreciate you giving us a very insightful presentation. We thank you for that. And appreciate taking time to join us, everybody. Just before we end, it would be nice if you could turn your cameras on, and I could take a screenshot of the for student chapter. So if you could turn it on for a second, let me take a screenshot. I'll just wait there one more second. See. Okay, I think I have.
Yeah, it's fun to see all of your faces. So I'm glad you're turning your cameras on.
Yes, just don't turn it off for a second. Okay, hold on. It takes me a second to take a screenshot. And
Yeah, I'm going to use my camera and take a picture of my screen.
yeah,
And I want to thank you for joining our EERI Friedman Family Visiting Professional Program presentation today. It's been enjoyable for me to visit with you. I enjoyed visiting with your student chapters. If you're not a member of the EERI student chapter, I encourage you to join. And you saw the benefits that will happen after you graduate, as well as the benefits you get as a student. And I appreciate the University of Memphis and all that you're doing to help reduce the risk of seismic events. And I encourage you to continue your progress in learning. That's the great thing about this field that we've chosen, is it's always learning. I've been in the field for a long time, and I'm continually learning, and I'll never stop. It's always evolving, and there's great things to learn. And so reach outside of your comfort zone, and I'm excited for your journey. So thank you for letting me join you as part of this ERA presentation.
Thank you so much, Mr. Maxfield. And it was great having you between us, and on behalf of ERI student chapter, I can say we really enjoyed from this talk. Thank you so much.
You're welcome. So take care and enjoy your day, and success in all of that you're doing. And hopefully when this COVID ends, we'll be able to visit in person sometime.
Hopefully, thank you.
if you need a PDH, make sure you email me. Thank you. All have
All
a
right,
good day.
thank you.
Thank you.
Thank you.
Bye-bye.
Bye.
Thank you all.